All right, welcome back. So we're going to consider shafts that are subjected to only twisting moment, and that's a continuation from our last lecture. So here, the first equation that we're going to look at that will help us to derive an expression for the in determining the size of that shaft subjected to only twisting moment is this equation right here. T divided by J equals tau on R. The T is the twisting moment or the torque that is acting on the shaft. Then we have the J to be the polar moment of inertia of the shaft about the axis of rotation. Then the tau is the torsional shear stress on the shaft. Then we also have the R, which is equal to the radius, that is the diameter divided by 2. And that's the distance from the axis, the neutral axis, to the outer fiber or the outermost fiber of the shaft. All right, now I believe this equation is not new to you. T on J equals tau on R. It's something that I believe you've done in a strand of material. All right, so we're just going to use that in sizing the shaft. So let's try to digest further this expression, this equation. The J, which is the polar moment of inertia, is equal to pi on 32 times d exponent 4, where d is the diameter of the shaft. And then the T, which is the torque, is equal to pi divided by 16 times tau times d exponent 3. And this equation here is an expansion of this one where we put the J, we substitute the value of the J into this equation, and then we made the T the subject. When you make T the subject, you're going to get this expression here. And this will stand for a solid shaft. So when the shaft is a solid shaft, um, and the diameter of the shaft is D, and then we have the shear stress in the shaft to be tau, the torque is related to the diameter with this equation. So the torque is equal to pi divided by 16 times tau times d exponent 3. And in cases where we have a hollow shaft which is subjected to only twisting moment, in that case the J will change. So the expression for the J is given in this equation here. So we have J is equal to pi on 32 times d exponent 4, sorry, d naught exponent 4 minus di exponent 4, where d naught is the outer diameter of the shaft, and then the di is the inner diameter of that hollow shaft. If we substitute this value of J into the equation here, we are going to have T to be equal to pi on 16 times tau. In bracket, we have d naught exponent 4 minus di exponent 4 divided by d naught, and that gives us the expression for the torque. All right, and then if we simplify it further, we are going to have the torque to be equal to pi on 16 times tau in bracket d naught exponent 3, and then in bracket again we have 1 minus k exponent 4, where k represents di divided by d naught. So k is the ratio of the inner diameter to the outer diameter. Di over d naught is k. Then we know that if we have twisting moment, and as we are aware that shaft is used to transmit power from one point to the other, then there should be a relation between the torque and in the power, and they are related by this equation here. We have P is equal to 2 pi n times T divided by 60. So we have the T to be the torque. N is the rotational speed of the shaft. So P is equal to 2 pi N times T divided by 60. And that's the relation between the power and then the torque, as well as the now let's look at this example. So example 1 says that a line shaft rotating at 200 rpm is to transmit 20 kilowatts. The shaft may be assumed to be made of mass steel with an allowable shear stress of 42 megapascals. Determine the diameter of the shaft, neglecting the bending moment on the shaft. So here, the shaft is made of mass steel with allowable shear stress of 42 megapascals. Is carrying an amount of 20 kilowatts and running at 200 rpm. And we are to determine the size of the shaft. So the assumption is this shaft is transmitting only power, is carrying only torsional um, moment, is transmitting only power. So there's only torsional moment, which is torque, and that is what is causing the shaft to rotate at that speed. So first, let's try and highlight the information that have been given. So we have 220 kilowatts, and then we have 42 megapascals. So we have the speed of the shaft, say N, is equal to 200 rpm. We have the power P to be equal to 20 kilowatt. Then the allowable shear stress is equal to 42 megapascals. And we have to determine the size of the shaft. So to determine the size of the shaft, we know that the equation T equals pi on 16 times tau times d cube is what we have to use. All right, so if that is the case, then we need to determine our T. We need to determine the T. Tau, we know it has been given to us already. We know tau. All right, so we already have this value. Then D is what we need to determine. In this case, that is what we are to find. So what is the torque on the shaft? We can calculate the torque by using the equation P is equal to 2 pi N on 60 times T. All right, so we have 2 pi nt divided by 60 will give us the power. So from here we can determine T. So here T will be equal to, you can say that T is equal to 60p divided by 2 pi N. And if you put in the values here, 60 times 20 times 10 exponent 3 divided by 2 pi times 200 RPM. Alright, so if you simplify this, you obtain the torque to be equal to 954.93 Newton meters. Then with this value here, we now determine the diameter D. Alright, so here if you make D the subject of the equation for the shaft, this equation here, then we are going to have D to be equal to the cubic root of 16t divided by pi times tau. So this will give us this equation will give us the value for the diameter D. So if you simplify, let's put the values inside. We have the D to be equal to cubic root of 16 times 954.93 divided by pi times tau, and tau is 42 times 10 exponent 6. So that is 42 times 10 exponent 6. That's megapascals. And if you compute that, we will have the diameter to be equal to 0.0487 meters. All right, and that is equivalent to 48 is equal to that's equal to 48.7 millimeters. And this value that we have here, if the shaft is having this diameter, it will be able to transmit that amount of power without any problem. But then this is not the standard size, so we need to determine the standard size of this shaft by using a table. So there is a table which can give us the standard size of the shaft that we can use. All right, let me quickly get that table. So when we go to that table, we have to select the size that is standard, and the size that you select, you make sure that that size will not be smaller than the size that we have calculated for. If it is smaller than that, it means that the shaft may fail. All right, so let's look at this table. So we have this table here, and you will see that the value that we got is 48.7. 48.7. All right, but on the table in millimeters, that value lies between 45 and 50. 45 is too small for the theoretical value we are having. So we have to select a standard size that is the next standard size that is bigger than 48.7, and that is 50. So that side is 50 millimeters here. So we select that as the size for the shaft. So you can say that our D is approximately 50 okay, our D is approximately 50 millimeters. Thank you. Let's look at the next example. So let's look at the next one. Okay, so we have the next one here, and it says a solid shaft is transmitting 1 megawatt of power at 240 RPM. Determine the diameter of the shaft if the maximum torque transmitted exceeds the minimum torque by 20%. Take the maximum allowable shear stress as 60 megapascals. So again, we have been given the power being transmitted, the speed of the shaft, we have the allowable shear stress, but there is some percentage, 20%, which has been given. And that is saying that the torque may exceed, the maximum torque may exceed the main torque by 20%. So let's pen down the values given. First, we have power equals 1 megawatt. We have the speed of the shaft to be 240 RPM. And then we also have the shear stress. The allowable shear stress is 60 megapascals. Then there is some percentage given. So let's say T mean, we call the mean torque as T. And then the maximum torque, we don't know the mean torque. The maximum torque, let's say that is T max is equal to 20% more than the mean torque. All right. So 20% more than the mean torque, it means that the maximum um, torque is equal to 1.2 times the mean torque T. All right. Then with this information, we need to determine the diameter for the shaft D. That one too, we don't know. So let's first of all determine the torque, because we have an information for the shear stress, the speed, and the power, but we don't know the mean torque. The maximum torque we also don't know. But if we calculate the mean torque, we can determine the maximum torque. Then we can determine the diameter from the diameter shaft design equation. So from here, we can say that the torque T is equal to 60 P divided by 2 pi n, and this will give us 60 times 1 times 10 exponent 6 divided by 2 pi times 240 rpm. Then when you calculate this information, we are going to get 3 9,788.736 Newton meters. Then from here, we can determine the maximum torque. So T max will be equal to 1.2 times 3,978.736, and that should give us 47746.483 Newton meters. Now we can determine the diameter of the shaft. And as determined earlier, if we make D the subject from the shaft equation, we have D to be equal to the cubic root of 16T divided by pi times tau. In this case, is the maximum torque that we are going to use. So say T max. All right. Then if we put the values, we are going to have D to be equal to the cubic root of 16 times 47746.483 divided by pi times the tau, allowable shear stress, is 60 times 10 exponent 6. And if we compute this, we are going to have the value to be equal to 0.159 meters as the diameter for the shaft. And this is the same as 0. Is the same as 159 millimeters. All right, but 159 millimeters on that table, if we check on the table, we don't have 159 millimeters, but what we have is what we have is 160. So if we look at the table, we can see here that the 159 millimeters is fall between 140 and 160. 140 is too low, so that is out, and 160, that's okay. Slightly large, so it's safe and it's not too much over designed. All right, so we can go with 160 as the standard value for the shaft size. So we can say that this D is approximately 160 millimeters. All right, so this becomes the answer for the size of this particular shaft. Now this 20% is necessary in the design. That may not be the operating torque of the shaft. This maximum torque may not be it's not the operating torque of the shaft, but at times in loading of the machine element, this torque could be resistance. We have what we call starting load or overload. And usually when the machine is still, is not moving, is static, and we are putting it to motion, the torque required to set it into motion may be higher than the normal running torque of the machine. So usually this torque is higher than the main torque, the normal running torque, and that is where the 20% increment may come in. So in this particular case, when you are designing the shaft, you have to take into consideration that increment during the starting of that machine element, so that the shaft may not be under design. Because if you have designed using the main torque, which is lesser than this maximum torque we are talking about, and you subject the shaft to this high amount of torque, which is the maximum torque, the shaft may end up failing in the process. So if you design and then you take that overload into consideration, then your shaft will be able to satisfy the operating conditions of the machine. All right, we are going to look at the next um, we are going to look at the next one. And yeah, I'm, I'm I'm doing some recording. All right, so in this case, we have a shaft that is to transmit 20 kilowatt at 200 RPM. So we have 20 kilowatt to be transmitted at 200 RPM. The ultimate shear stress for the steel may be taken as 200 megapascals. And the factor of safety 8. If a hollow shaft is to be used, in place of the solid shaft, find the inside and outside diameter when inside and outside diameters when the ratio of the inside to outside diameters is 0.5. So we have to determine first of all the diameter of a solid shaft that will be used to transmit this amount of power, 20 kilowatts. So let's put in the information down. We have power to be transmitted to be 20 kilowatt at a speed of 200 RPM, and allowable the ultimate shear stress. So the shear stress, say tau ultimate, is equal to 360 megapascals, and the factor of safety, so say SF, is 8. If a hollow shaft is to be used, so first of all we have to determine the diameter of the solid shaft. When we finish, we can determine the diameter of the hollow shaft. So the hollow shaft, we're given the ratio of the inside to outside diameters to be 0.5. So that is the value K is equal to the inside diameter di, or the outside diameter d naught, to be 0.5. All right. So here we first have to determine, we can also determine the allowable shear stress. So we're giving factor of safety. So factor of safety is 0.8, and the ultimate shear stress is given as 360 megapascals. So if you want to determine the allowable shear stress, tau, or tau allowable, is equal to the ultimate shear stress, tau ultimate, divided by the factor of safety. And if we put in the values for this one, we're mainly going to have 360 over 8, and that will give us 45 megapascals. So this will give us the value for the allowable shear stress. That's the shear stress we'll use in determining the size of the shaft. All right, so let's start with the computation. Again, we have to determine the torque. So the torque to be transmitted in this case for this solid shaft T is equal to 60p divided by 2 pi n, and that is 60 times 20 times 10 exponent 3 divided by 2 pi times 200. And when you compute that, we get 954.93 Newton meters. Then after that, we can determine the diameter, and we already know that the diameter for the solid shaft is equal to the cubic root of 16t divided by pi times the shear stress tau, and in this case is the tau allowable. So that is our allowable shear stress here. And then when we compute this, let's substitute the values inside and compute. So we have cubic root of 16 times 45 times 10 exponent. Sorry, it's 16 times the torque, which is 954.93 divided by pi times 45 times 10 exponent 6. And when you key in, we're going to get 0.048 meters, and that is equal to 48 millimeters. All right, and on the standard table, this value, we can say that D is approximately 50 millimeters, approximately 50 millimeters. Now, having determined this, we can determine the inner and then the outer diameter for a hollow shaft using the information given. So for a hollow shaft, for a hollow shaft, we have been given K. K have been given to us as 0.5, and we know that the torque for a hollow shaft is equal to pi divided by 16 times tau, the shear stress, in bracket D naught, which is the outer diameter, cube, and then open another bracket 1 minus K exponent 4. That is the equation for a hollow shaft. Now from here, we know tau, we know K, it has been given to us, but we don't know D. All right, so we don't know D, and D is what we are to determine. So to determine D, we can make D the subject in this equation. And we can say that, we can make D not the subject in that equation. We can say that D naught is equal to the cubic root of um, 16t divided by 1 minus K exponent 4 times pi times tau. Then we put in the values for this, and that will give us the cubic root of 16 times the torque, The torque, we know it already. We've calculated the torque to be equal to this. So we have the torque to be 954.93 divided by 1 minus 0.5, that is the k exponent 4 times pi times tau, and tau is 45 megapascals times 10 exponent 6. All right, so if we compute this, we are going to get d naught to be equal to 50. It will give us 0.049 meters, all right, which is equal to 49 millimeters. And this value here, of course, is not a standard value. We can say that on the table. This we can conveniently use 50 millimeters. So we can say that D is approximately 50 millimeters. Then from here, we can determine, this is D naught. From here, we can determine DI, which is the inner diameter. So DI will be equal to, we know here that K is equal to DI over D naught. So DI will be equal to 0.5 D naught, and that is 0.5 times 40, 0.5 times 50, and this will give us 25 millimeters. So we have DI is equal to 25 millimeters. All right, so again from here, this information we are having, we can see some happening here, that the D naught, for which is the outside diameter for the hollow shaft, is the same as the diameter for the solid shaft, also 50. All right, but the hollow shaft is having some void inside of diameter 25, which means that the hollow shaft will have lesser material compared to the solid shaft, and yet it will be able to perform the same function as the solid shaft in terms of carrying the same amount of power, just as the solid shaft. Are you getting it? So the hollow shaft is stronger in this particular application. All right, thank you very much. See you later.